Good morning. Today we're going over our first homework assignment for nuclear chemistry, and this should actually be pretty fun after we did all of that acids-base stuff. This is going to be the easiest thing you've ever done. And in fact, the first couple problems are a throwback to chapter 2 or 3 at the beginning of the semester when we were looking at the periodic table and assigning things like protons, neutrons, and electrons. That's all we're doing here. So for this first problem, for instance, they say we've got Al27 and they want protons, neutrons, and electrons. And that little 27 means we're looking at the specific isotope of aluminum that has a mass of 27. So here we go. We can say if we look at our periodic table, we're going to zoom in here on aluminum. Aluminum has an atomic number of 13. And for the moment, we're going to ignore this because this is an average weight. And here we're looking at specific isotopes. So this has a specific weight. So we've got aluminum. Every aluminum, by definition, has 13 protons. So we can say, all right, I've got aluminum. It has 13 protons. And if my mass is 27, remember that mass is the number of protons plus neutrons, because protons and neutrons are the only subatomic particles that have any mass. So if my total mass is 27 and I have 13 protons, then that means I've got 27 minus 13. It looks like I've got 14 neutrons by definition. Now if I'm neutral, the electrons would be the same as the protons. Remember, charge then, and this is again in our lecture notes from our chapter on the periodic table, but the charge is the number of protons minus the number of electrons. So if I have 0 charge, then I've got to have the same number of protons as electrons. So in this case, because I'm aluminum 27 and they don't tell me that I've got a charge, I'm going to assume that I have the same number of electrons as protons. So if they want protons and then neutrons and electrons, I've got 13 and then 14 and then 13, and that is what they're looking for. It's not any more difficult than that. In this case, I've got silicon 28. And so silicon, in this case, the mass always goes in the top left. The atomic number goes in the bottom left. And you don't always need to put the atomic number here because it's on the periodic table, right? Silicon, by definition, is number 14. But it's really convenient to put it there because we're going to be doing math with those. So it's nice to just have that number handy. So it's telling us that the silicon has a mass of 28 and 14 protons. So, okay, if I know that my silicon has 14 protons and a mass of 28, which is the sum of my protons and neutrons, that means I've got 14 neutrons too, because 14 plus 14 is 28. And then again, there's no charge, so by definition, I must have the same number of electrons as protons. So 14, 14, and 14. Here, B11, that's boron with a mass of 11. Our periodic table tells us that boron has 5 protons by definition. So boron, 5 protons, a mass of 11, which is the sum of my protons and neutrons, so that must be 6 neutrons, because 5 plus 6 is 11. And again, there's no charge, so I'm going to say same number of electrons as protons, 5, 6, 5. And if you're looking at this on a test, just make sure that you're going in the order that I'm asking it, right? Because if I ask for protons and then electrons and then neutrons, I'd have to reorder those. So careful of that. And the last one here, we've got mercury, 199. That means mercury with a mass of 199. And we've got here 80 protons. And again, please do not make the mistake of going to the periodic table and saying, oh no, mercury has a mass of 200 or 201. No, no, no. This isotope of mercury has a mass of 199 because we're looking at a very specific isotope and not the average of all mercury isotopes as existing in a natural sample, which has this particular weight. Careful on that. So mercury, they're telling us it has 80 protons, and that is by definition, that's on the periodic table, but again, it's convenient that they gave that to us. If the mass is 199, then 199 minus 80, that tells us we have 119 neutrons, because that's where all the rest of the mass came from. 119 neutrons. And then again, if I'm neutral, I'd better have 80 electrons. Here we go. 80, 119, and 80. All right. Now symbols for the following isotopes. If I have 6 protons, then by definition, atomic number 6, I'm carbon. And then if I have 8 neutrons, then my total mass is the sum. So 6 plus 8 is 14. So I'm carbon with a mass of 14. And by definition, I have 6 protons. So here's my mass of 14 that goes on top. Atomic number of 6 that goes on bottom. And my symbol, capital C for carbon. Here, if I have 19 protons, then by definition, on my periodic table, my atomic number, 19, that makes me potassium. So they told me I've got a mass of 39 in this particular isotope, and 19 protons. Symbol for potassium is a capital K. And the last one, mass of 26, 12 electrons. If I'm neutral, that means I also have 12 protons. Well, this is saying it's atoms, not its ions, so that's a valid assumption. And according to our periodic table, atomic number 12 is magnesium. So according to our periodic table, atomic number 12 is magnesium. All right, so what's the difference between a chemical reaction and a nuclear reaction? Really, when it comes down to it, chemical reactions happen on the surface of the atoms, which means that's where your electrons are. So your chemical reactions have to do with sharing or giving away electrons, whereas nuclear reactions occur in the nucleus. That's where you've got protons and neutrons. Because the chemical reactions happen on the surface, then you get some things like temperature changes or concentration changes or catalysts. Those can change the rate. But because the nuclear reactions are held inside the nucleus, totally shielded from all of that, then temperatures and catalysts and concentration changes totally do not affect the rate. The rate is completely independent of that kind of thing. So those are the kind of things we're looking for on the options here. So outer shell electrons, that's a chemical reaction. If my rate is not affected by temperature or catalyst, that's probably a nuclear reaction. Different isotopes have the same behavior, that's a chemical reaction, whereas different isotopes have different behavior, that's a nuclear reaction. So that's something like carbon-13 is going to behave differently than carbon-12 in the nuclear reactions because they have different nucleuses. But for chemical reactions, they're going to behave the same because they have the same outer shell electrons. Chemical reactions never produce different elements, but nuclear reactions usually do because you're actually changing what's in the nucleus, which defines what the element is. Here, rate can change with temperature or catalyst. That would be chemical reaction. Rate is the same whether the atom is in a compound or uncombined. That's because the nucleus has no idea what's going on the surface, so it just does whatever it wants no matter what condition it's in. And finally, this involves a change in the atom's nucleus. That would be a nuclear reaction by definition. Next, we're looking at different types of particles and radiation types for certain nuclear reactions. The 42He is a helium nucleus, but it's also known as an alpha particle. They named it as an alpha particle before they knew what it was. So it's both a helium nucleus and an alpha particle. That 0 positive 1e looks like an electron, but the positive charge tells you it's a positron, positive version of the electron. And that 0, 0, this is the Greek letter gamma. That is a gamma ray. It has no mass, it has no charge, but it has an enormous amount of energy. The 0, negative 1e is an electron, also known as a beta particle. Again, they discovered this and named it before they had an idea of what it actually was. So it's a beta particle. It is also an electron. That little negative charge down there tells you that it's got a negative charge. That means it's an electron. The H plus, that is a proton, because it's just hydrogen comes in with one proton and one electron. So if I lost my electron, then all that's really left there is a proton. And this is a neutron because it has a mass of 1 but a charge of 0. Another way that we express that. Now for types of radiation, the alpha particle, beta particle, gamma ray here, they have different properties, and it's based mostly on their mass. The alpha particle is a helium nucleus, so it has a mass of 4. The beta particle is an electron, so it has a mass of about 0. It's not actually 0. It's actually 1/2000th of an atomic mass unit, which is why we say electrons don't really have appreciable mass next to a proton. But a gamma ray truly has 0 mass because it is not a particle, it's just energy. Now the difference in mass is what gives you the difference in penetration power and the difference in danger, essentially. So deepest penetration is something without mass because it's hard to stop something that doesn't have any mass to stop. Something with a larger mass is not going to penetrate as far because it's easier to stop it. It's a bigger bullet, essentially, or it's a bigger particle. Of course, that's in the middle. Your gamma ray is neutral. Beta particle is an electron, so it has a charge of -1. Alpha particle is your helium nucleus, so it has a charge of +2. And then, of course, based by speed, same thing. If I don't have any mass, it's easy to go fast. If I do have lots of mass, then I'm going to go slowly. And in the middle, then I'm going to go relatively in the middle. And here again, gamma is going to penetrate the farthest because it has no mass. That also makes it a lot more dangerous than the other stuff because you can block the other stuff a little bit more easily. So for instance, a beta particle, I can block that if I have lab coat and gloves. Also the alpha particle, because that's even slower. Whereas travels a short distance in air, that's an alpha particle because it's so much heavier than the rest. All right, so now we're going to look at the type of decay and classify this based on what other particles we see being released. So here, 27M aluminum decomposes to form 27 aluminum. This is like a metastable version, just has extra energy attached. Here it's dropping that energy. You can see that is a gamma ray, so that would be gamma radiation. Boron 8 decomposes to form beryllium 8, and it loses this 0 positive 1e, that's a positron, so that would be positron emission. Strontium 90 decomposes to form ytterbium 90, and looks like we've got an electron here, which is also known as a beta particle. It's the negative charge, so that would be beta decay. And finally, we've got astatine 218 decomposes to form bismuth 214, and a alpha particle, also a helium nucleus. Those are the same thing. So that's alpha decay. If you can predict, if you can classify these, then you're in good shape. Same story. Oh, in fact, these two are exactly the same. but some of these are randomized, so you might have different options. That is, again, gamma radiation. Again, there's a positron emission. And here, there's my alpha particle. So that's going to be alpha decay. Okay, now we're going to predict what else is formed. And this is actually really easy because mass is always conserved and charges are always conserved. So the mass on the left has to equal the mass on the right, and the total positive charges on the left have to equal the total positive charges on the right. So 60 is going to equal 60 plus whatever this is, which must be 0, right? And 27 is going to equal 28 plus whatever this is, which would have to be -1, right? 28 minus 1 is going to give me 27. So whatever this particle is, it has a mass of 0 and a charge of -1. 0, -1. And then you can tell me what kind of a particle has a mass of 0 and charge of -1. That's an electron. Looks like that. That's a beta particle. Now, what else does this turn into? 18 has got to equal 0 plus whatever the mass of this is. So the mass of the product is 18. 9 has to equal the 1 plus whatever goes here, which must then be 8. So this is going to be 18, 8. And then I just look on the periodic table and say, which atom has atomic number 8? And that is oxygen. So, here we go. O for oxygen. Next, if I'm going to predict the reactant that I started with, again, whatever the mass is has to equal the total mass on this side. So 59 plus 0 gives me a mass of 59. And then the bottom number has to be the sum of these bottom numbers. So 27 minus 1 is 26. 59 on top, 26 on the bottom. And then I look on my periodic table to see which is element number 26. It's iron. All right, now if I want to write the entire equation and they want alpha decay, I'm going to start with this guy and do alpha decay. So 243, 96, curium goes to form. The alpha particle is my helium nucleus, 42, He. And then, all right, so 243 has to equal the sum of 4 plus, looks like it's going to be 239. 239 plus 4 is 243. And 96 must be the sum of 2 plus, that would be 94. And I look on my periodic table and see, 94, that's going to be plutonium, Pu. So that would be the balanced nuclear equation for the alpha decay of curium 243. Copy that. And then insert that here so I can just edit this. 252, 99, ES. Still doing alpha decay, so that's what I get. And then 252 minus 4 is 248. 99 minus 2 is 97. And element number 97 is berkelium, Bk. Your isotopes are likely different than mine. So don't copy what I'm doing, but copy the process. That's what you should be doing. Element 251, 98, californium, decomposes by alpha emission. 251 minus 4 is going to be 247. 98 minus 2 is 96. And element number 96 was curium. these equations are almost therapeutic compared to the craziness that was acids and bases. Not that acids and bases are crazy, but they're a lot of work and there's a lot of different moving parts. Whereas here, it's just kind of a simple balancing thing. Here we have element number 107, BH, decomposes by alpha emission. 261 minus 4 is 257. 107 minus 2 is 105. Of course, you'll have a calculator, so if you are not sure of your ability to do that kind of addition and subtraction, feel free to use your calculator. Dubnium, DB. This is like chemistry meditation. All right, now we're going to do balanced equation for beta decay for each of these. So if I have, I just find this easier to edit than to start a new one. 44, 19. Potassium. Beta decay is a beta particle, which is an electron. So it has a mass of 0 and a charge of -1. It just looks like that. And then 44 equals 0 plus 44. And 19 equals -1 plus 20. And element number 20, here we go, that's calcium. I'm gonna copy this one new. Here we go, iron 59. Iron is element number 26. So if I'm iron 59, I have a mass of 59. I have 26 protons, and Fe, beta decay, I'm losing an electron from the nucleus, which means my mass stays the same. 59 is 0 plus 59. And 26 equals -1 plus 27. And element number 27 is cobalt. That's what I get. Iron 60. If I start with, oh, I should have copied and pasted this one. Let's see if I can. Oh, no, I can't. So iron 60, if I have a mass of 60, and 26 protons. Fe for iron, beta decay, 60 equals 0 plus 60. 26 equals -1 plus 27. And element number 27 is cobalt. So these two were the same. I just had an extra neutron, but that didn't change the rest of it. Last one, barium 141. And barium is 56. Goes to form 0, -1, E, that's my beta particle, and 141 equals 0 plus 141, and 56 equals -1 plus 57, and element number 57, where are you? Right there. Lanthanum. So this next problem, same thing, but now we're doing positron emission. So we start here. We've got calcium 38. Goes to form our positron, which has a mass of 0 like the electron, but a charge of +1 instead of -1. And now our mass 38 has to equal 0 plus, in this case now 38, And 20 needs to equal 1 plus 19. And element number 19 is potassium. If I'm doing positron emission from carbon 11, and I start with a mass of 11, 6 protons, that's carbon, there's my positron, 11 equals 0 plus 11, 6 equals 1 plus 5, element number 5 is boron. Finally, we've got rubidium 79. There's my positron. So I'm going to need a mass of 79 in my product and 36 protons now. And element number 36 is krypton. Okay, so balanced equation for each of the following emissions. If I do an alpha particle, a beta particle, a positron. Okay, we've done this before. Let's try. We start with Hg 180. And that 180 is always referring to the mass, because Hg is by definition mercury, which has 80 protons. All right, and if I did an alpha particle, then this is actually 42He. It's a helium nucleus. And 180 equals 4 plus 176. And 80 equals 2 plus 78. And element number 78 was platinum. A beta particle from tin 126. All right, we'll start with tin 126. Sn over here, it's number 50. Beta particle is an electron, so I've got a -1. And 126 equals 0 plus 126. 50 equals -1 plus 51. And element number 51 is antimony, Sb. And finally, a positron from manganese 49. Got a mass of 49. Manganese is, by definition, number 25. Positron has a mass of 0 and a charge of +1, so that's my positron. 49 equals 0 plus 49. 25 equals 1 plus 24. Element number 24 is chromium. So that's it. And let's do it again. And again, these are probably randomized. You might not have the same ones as me. GD 148. GD is by definition where are you? There you are. Gadolinium, number 64. And if I'm doing an alpha particle, then that gives me a mass of 4, charge of 2, and I'm a helium nucleus. 148 equals 4 plus 144. 64 equals 2 plus 62. And element number 62 is samarium, Sm. Beta particle from strontium 90. Oops, that didn't work. beta particle from SR 90. 90, and strontium is number 38. Beta particle has a mass of 0, charge of -1. It's an electron. And 90 equals 0 plus 90. 38 equals -1 plus 39. Element number 39 is yttrium. And finally, a positron from Al25. I've got a mass of 25, and aluminum is, by definition, up here. Where are you? There you are, element number 13. Positron has a mass of 0, charge of +1, and a little e, because it is the antiparticle to the electron. And 25 equals 0 plus 25. 13 equals 1 plus 12. And element number 12 was magnesium. That's it, you guys. Not any more difficult than that. I hope you enjoy this assignment. You have certainly earned an easy one. Have a great day.